Hello and welcome to this further maths support program online revision session on numerical methods. This particular lesson is about the solution of equations and it's the first of two lessons on this. So what we're going to look at in this particular lesson is the bisection method, the method of force position, which is also called linear interpolation, and fixed point iteration. And what the specification tells you to do is that you've got to understand what each of those methods looks like in terms of a graph. You've got to be able to solve equations to the required degree of accuracy, which depends very much on what the question asks for. And then you've got to understand when sometimes these things go wrong and why they go wrong. You're also expected to know a little bit about their convergence. You're supposed to know that fixed point iteration's got first order convergence and that Newton-Raphson generally has second order convergence. So what I'm going to do is look at a few questions, and our first question comes from January 2010 and it's the first question on the paper. So the first thing we're asked to do is to show that that equation has a root between 1.3 and 1.5. Once we've done that, we're going to use a bisection method to get an estimate, and it uses the phrase which is very particular to the bisection method where it talks about the maximum possible error. Once we've done that, it's going to ask us to think about what we'd do if we carried this on a little bit further and we wanted to reduce that maximum possible error. So, starting with what we had as our equation, the first thing I do with these is I always rearrange them so they're equal to 0. And I do that because I can then look for a sign change. So we were asked to check that the root was in a particular interval, so if I re-express that equation as fx equals 0, then if I put in one of the ends of our range, we have 1.3, so if I stick in x equals 1.3 I get a negative result. If I stick in 1.5 I get a positive result. Now the way that I do that on my calculator to make life easy is I type 1.3 and then I press equals, then there's a key with ANS on it, and if you type just 2 to the power of ANS plus a half the power of ANS minus 3, press equals, it does all the hard work for you. So I do write out the calculation that I'm doing, but I also let the calculator take an awful lot of the strain. And I've written these to 6 decimal places because on the mark scheme pretty much every answer, unless it's otherwise stated, will be written to 6 decimal places for the person that's marking it. Now what we have there is a sign change, so in the region from 1.3 to 1.5 there must be some sort of root because that function is continuous in that particular area. Okay, let's go back to the question. We've shown that it's got a root between 1.3 and 1.5. We now have to use a bisection method to find an estimate with a maximum possible error of less than 0.2. So we have a particular way of setting this up. We start off with a table. Now that table looks very complicated, but actually it's a pretty straightforward table. What we have is we have our two x values, so we know the answer is going to be between A and B. One of them gives us a positive result, one of them gives us a negative result, which this always ties in brilliantly with that sign change. So one of them had a negative and one of them had a positive result. So for 1.3 we had a negative result, and for 1.5 we had a positive result. Now interval bisection is pretty much what it says. We have an interval from 1.3 to 1.5 and we want to cut that in half. So we need to use a value that's exactly halfway between 1.3 and 1.5. Now you'll see here I've written C is A plus B over 2. The simplest way of calculating it is to add the two together and divide by 2, just the mean of those two values. In this case you can do it by sight. Halfway between those two is 1.4. So what we need to do is work out whether or not 1.4 is at the left of our interval or at the right of our interval, so we need to check and see whether it gives us a positive or negative result. So we substitute it into our function and we find out that it gives us a positive, and I do that letting the calculator take the strain. So I type 1.4 equals, and I had 2 to the power of 1.4 plus a half to the power of 1.4 minus 3. So I type that in and it gives me a positive. Now we come to the bit about maximum possible error. For the region 1.3 to 1.5, the answer is somewhere in there. Okay, so our 1.4, which is halfway between the two, at most can be the gap between 1.3 and 1.4, or the gap between 1.4 and 1.5. So the maximum it can be is 0.1, because between 1.4 and 1.3 that's a gap of 0.1, between 1.4 and 1.5 that's a gap of 0.1. And one way of thinking about that maximum possible error is that it's half of the interval. So from 1.3 to 1.5 is a gap of 0.2, so the maximum possible error is 0.1. And that will keep halving each time. So we know that we want to get to a stage where our maximum possible error is lower than 0.02. So what I do is I halve it and keep halving it until I get my first value that's lower than 0.02, and I know that that's where my table is going to finish. So I now go through, and the 1.3 hasn't changed because that's still at the left hand of our particular interval. The 1.4 replaces the 1.5 because that's at the positive end of the interval, and we now look for the value that's halfway between those two. So that's 1.35. So we've got 1.35, we substitute it into the function, and that's negative, which tells me I'm going to replace the 1.3 with the 1.35. The 1.4 stays as it is, and halfway between those is 1.375. And by this stage you might end up adding the two values and halving the result to get that. And then I substitute that into my function, and that gives me a negative. So I know that I'm replacing that one with 1.375, and the 1.4 stays as it is. And I've actually got to the end of this. The mid-interval of those is 1.3875. That's a value I'm going to use as my root, and that's the first time I've got a maximum possible error of lower than 0.02. So the root is 1.3875 approximately. Okay, let's look at what we have to do now. We've done the bisection method, and finally we've got to determine how many further iterations would be required to reduce that MPE to less than 0.001. So it's how many further. Just bear in mind that we've done so many so far, and it's how many more we're going to need. Well, we know that the MPE halves each time we go through it, so what we're going to do is keep halving until we get lower than 0.001. So we're at this at the moment, so we halve, and we get that, then we halve, we get that, still not lower than 0.001, halve again, still not lower, but when we halve again, we get that. So we count up how many halvings we had to do, and that's 4 of them. So there's 4 more iterations that are required, and so we write that down. So let's have a look at the marking. Pretty usual marks for checking for the position of a root. There's one for the method and one for the answer. Now, quite often on the mark scheme, they don't compare to 0. I always find it better to compare to 0 because it fits in with the next stage. But on the mark scheme, they might say calculate 2 to the power of 1.3 plus a half to the power of 1.3, and then compare it to 3 and see if it's lower, and then calculate the same with 1.5 and find out that it's higher than 3. So if one's lower than 3, one's higher than 3, that shows you the roots there. But I find a sign change is a far more reliable way of doing that, and it sets it up very nicely because this function here is in fact the function that we're going to use in our interval bisection. So I always like to use a sign change for this. For our table of values, there's one mark for the method, which is pretty much the top line of the table, showing that you know pretty much that it works by looking for an interval and comparing the values, gives you that one mark. You then get an answer mark for each subsequent line of working. So for the next line of the table you get A1, for the next line you get A1, and then finishing at the right place also gives you an answer mark. Okay, so the final stage was how many more iterations, and there's one for the method and one for the answer, and that's fairly standard on those exam papers. The next question we're going to look at is January 2010, question 7, so this is in section B, and this is a far more involved question. So let's go through how we do this. First thing it asks us to do is to show that an equation has a root in the interval pi by 2 to pi by showing the graph. So I'm going to sketch the graph first, and I'll do that now. So put in my axes. I know the shape of sine of x, so sine of 3x is basically going to go up to 3. I know that it's going to cross at 180 or pi, and so my graph looks like that. Now, that's just 3 sine x. We're trying to find out something about x equals 3 sine x, so I draw the graph of y equals x. And what we've got to do is say that it's got a root in the interval. So we need to show that where they cross is in that interval. So my diagram clearly shows that. Now, there is only one crossing point there because the diagram shows it, but then it asks us if there are any other non-zero roots. Well, there is one other, and the reason for that is if I carry on my graph in the other direction, I'll get a negative result. So I've shown a diagram to make the explanation clear. Now, part 2 asks us to iterate it. So I'm going to flip back to the question very quickly. Part 2 says determine whether or not the iteration x r plus 1 equals 3 sine xr, starting with x equals 2, converges to that root, and then illustrate the answer with a staircase or cobweb diagram. A lot of marks for doing this. Okay, so showing the iteration in a table is usually a good idea. So we're starting off with our first value as 2. Now the way that I do this is I type 2 equals, and we had xr equals 3 sine x. We're working in radians, so make sure your calculator is set to radians. And so what I do is I write 2 equals, and then I write 3 sine answer and press equals, and that gives me the 2.727892, again rounding that to 6 decimal places because that's what's on the mark scheme. However, because of the way that I've entered it using the answer key, I can just press answer again, and I press equals again, sorry. If I press equals again, I then get the next result to 6 decimal places. I then press equals again, and I get the next result, which I write to 6 decimal places, and I press equals again, and it doesn't look very hopeful. In fact, you can see from that if I keep pressing equals, it's not going to converge. It seems to be jumping between the two values, and it's getting further away each time. So it's oscillating between values that are getting further and further apart. So it doesn't converge. I've got to show that on a cobweb diagram. So here's my original graph that I had drawn, and the first value started off with was x equals 2. So the way this works is that we calculate 3 sine 2. We then use that as our next value that we're going to substitute in. So if I project onto line y equals x, that means that x is now that 2 point whatever that we had before. And so if I work out the new y value, I end up going to there. And I use that as my new x value, sub it in, new y value, and by this stage I've shown that I'm getting further and further apart. And you can see that it's oscillating because it gets further and further apart, and it keeps getting one to the left, one to the right. And that would be enough for the cobweb diagram for that question. Okay, so that's part 2. Then part 3 asks us to show that the equation can be rearranged into x equals sine x plus 2/3 x. And we're going to start again with x naught is 2, but this time I'm going to try and show that it converges rapidly and write the answer to 5 decimal places. The final thing it asks us to do is to verify that it's correct. And there's a lot of marks because it asks us to do quite a lot there. So I've got to show some convincing algebra that shows it comes to that value. So first thing is, I saw that there was a third in there, or there's some thirds in there, so divided by 3 is quite a good idea. Next thing is I've got to try and get 2/3 in there. Now I know that that's 1 minus 1/3. So that 1/3 x there I can do as 1x take away 2/3 x, and I've suddenly got my 2/3 in there. And really for these you've got to read the clues of where you're heading for. So without those clues it's very hard to see what to do, so look at what you're aiming for and think, how can I possibly get it to look like that? And finally the stage is to obviously rewrite it as x equals sine x plus 2/3 x, which is what they want. Now we're going to use this as the iteration formula, and so what I'm going to do is do the same trick, but this time I'm going to show that it converges very quickly. So again with a table, starting value of 2, and I do the same trick. I do 2 equals, and then I do my sine answer plus minus 2/3 answer, or is it plus 2/3 answer? Can't remember, but I do the correct thing. Let's just flip back. Yep, so I do sine answer plus 2/3 answer. So I wrote 2 equals sine answer plus 2/3 answer. When I press equals, first time through I get that to 6 decimal places, 2.242631. Press equals again, and you can see pretty quickly that I'm ending up with something that's almost identical by the time I get to the 4th and 5th iteration. So to 5 decimal places it's converging very quickly to 2.27886, which is what both 4 and 5 converge to. And I put in those stages, and I really had to put in those stages because those two both round to the same thing, to 5 decimal places. Okay, we've got to verify that's correct. Now I verify these things with a sign change again, because I like doing the sign change method. So we're talking about it converging to that. This is the equation that we're dealing with. So I'm going to say that fx is equal to x minus 3 sine x. And then to 5 decimal places, the lowest thing that can round up to 2.27886 is 2.2788855. So that's the lowest thing that can round up. And if I substitute that in, I get a negative value. Now the highest thing that could round down is something that's just below 2.278865. And so I substitute that in. If you like, they're the two ends of the interval that rounds to 2.27886 to 5 decimal places. One of them gives a negative, one of them gives a positive, which means that the value must lie between those two values, and everything that lies between those two values rounds to 2.27886 to 5 decimal places. So because we've got a sign change, it tells us the root is in that. So we can then say that alpha is that to 5 decimal places. Okay, so the marking for this. There's 2 graph marks for showing the 3 sine x and the y equals x with their intersection. There's 1 explanation mark for saying that there's only one other non-zero root. Okay, and it says state or show for that explanation mark. Now for showing that it doesn't converge, there's 1 method mark which will be clearly calculating some of the values. There's 2 answer marks for showing some of the values, so 2 more correct lines after the first one. And then there's a mark for saying that it doesn't converge. The cobweb diagram, you get 3 marks for doing that, which means that you have to show, I think, at least 2 more x values. So that's why I've got, in fact I've done 3 more x values there. I've got 3 vertical lines after the original line going up from 2. That's quite a good way of thinking about that, so there's 3 marks for that. Then, for that rearrangement, any convincing algebra gives you a method mark. You get 1 method mark for again doing your repeated iterations, an answer mark for each of a couple of lines of correct calculation, and then an answer mark for the correct value to 5 decimal places. For doing a sign change, you get 1 for the method that you use, one for the answers, which will be the substitutions that you do, and then one for that explanation that says that's why it's got a root in that, so it must be that to 5 decimal places. Okay, so the next question is May 2010, question 1, and it's another iteration one. This time it tells you it's got a root between 1 and 2, and it gives you an iteration, and then it asks you to show that that converges, but not to the root that's between 1 and 2. Okay, then you've got to find another iteration that does converge to the root between 1 and 2, and you have to demonstrate it by carrying out the stages. So this is a slightly easier question. So I'm doing the same thing as I do before, which is I'm going to rearrange it and put it equal to 0, and then look for a sign change. So I'm going to say the function of x is that left-hand side, so I'm looking for where fx is 0. So if I stick in 1, I get a nice easy calculation to do, which gives me -1, and if I stick in 2, again a fairly easy calculation, this time I get a positive. So because there's a sign change, there's a root in that interval from 1 to 2. So the iteration, again I do this by putting in 1.5 equals, and then I use the answer key. Now I'm going to run back to what the iteration is. It's 1 over 3 minus x squared. So what I do is I'll type 1.5 equals, then I'll do 1 divided by, or in fact I'd use the fraction key on the calculator, 1 over 3 minus answer squared. And in doing that, I would get 1.3 recurring for the first time I press equals. Next time I press equals, I get the 0.818. And you can see that it's converging, but it's not converging to something that's between 1 and 2. It's converging to something that's around 0.3-ish. So it's converging to a root, but that root isn't in that interval from 1 to 2. Okay, the question then says rearrange that original equation to find another iteration that does converge to the root between 1 and 2. Now I'm going to show you one possible iteration that you could use, one possible way of rearranging the formula, but it's not the only one. So I've rearranged it so I get x squared equals, and I've just taken the square root, which means I get that iteration formula. If I try that in my table by pressing 1.5 equals, then doing the square root of 3 minus 1 over answer, each time I press equals I get those values in the table, and you can see that it's converging to something between 1 and 2. It's converging to 1.532, and that's pretty much what we wanted. It's converging to that root. Okay, so let's look at the marking for it. For the first bit, there's 1 mark and 1 answer mark for looking for the sign change. Okay, so that's a fairly usual marking scheme for confirming that the root is in that interval. 1 method mark for your iterations, an answer mark for getting some of that right, and then an explanation mark. The rearrangement for part 2 gives you 1 mark, and again 1 method, 1 answer for showing that it converges to a root in 1, 2. So that was quite a quick question. Now January 2011, question 1. Again, we've got to show something as a root in a certain interval. We've got to show an iteration diverges, and then we're going to find the root to 3 decimal places. And this has only got 6 marks on it, so this should be a fairly straightforward question. So we're dealing with that. Make sure we're working in radians. Rearrange it. fx equals the left-hand side. Put in 1 and I get a positive. Put in 1.2 and I get a negative. So the sign change confirms that I've got a root in that region. Next thing I've got to do is show that the iteration that they've written there diverges. So I'm going to type in 1.1 equals, then I'm going to do tan answer minus 1. Okay, so there's my table when I do tan answer minus 1, press equals each time. And I think by the time you get to step 5, you can see there's a bit of clear divergence there. Okay, so it diverges. Finally, I've got to use another iteration to find the root correct to 3 decimal places. So I'm going to try something else. I'm going to do an inverse tan, which gives me that iteration. So when I try that, I put in 1.1 equals, and then I do inverse tan of 1 plus answer. Each time I press equals, I get those values, I've written them down to 6 decimal places, and I get an answer from, in fact, 3, 4 and 5, 1.132, so the answer must be 1.132 to 3 decimal places. Okay, marking for that, again, one method, one answer for looking for the sign change. One method, one answer for showing that divergence. One mark for rearranging it to something that will converge. And then for our final convergence, we have one method and one answer mark for the table and an answer mark for the final value to 3 decimal places. Next question is from May 2011. It's question 1. And we have a continuous function. It's got a root between 0.4 and 1.8. We're going to find that root using the bisection method. But the first thing it asks is something a little bit different. It says state the best possible estimate of the root at the start of the process. Then it says state the maximum possible error associated with that estimate. And then it asks you to try out or find out how many iterations are needed to reduce that MPE to lower than 0.05. And then for part 2, it asks us to do the final thing that we haven't really done from what I said I'd cover, which is the method of false position. So the best estimate is 1.1. The reason for that is because that is exactly halfway between 0.4 and 1.8. You can find that out by adding the two together. If you add the two together, you get 2.2, and halve it, you get 1.1. So 1.1 is exactly halfway. So that's the best estimate. The maximum possible error on that is half of the interval. Okay, so the interval is from 0.4 to 1.8 is 1.4. So half of 1.4 is 0.7. The other way of thinking about that is 1.1 is 0.7 away from either end. Now, we know that the maximum possible error halves, so we keep halving it until we get lower than 0.05. And to do that, we've halved 4 times, so there'll be 4 iterations needed. Okay, the second bit is the method of false position. I've got a particular way of doing that. Basically, look at what we have here and here. I like to imagine them as x and y's. So when x is 0.4, y is negative 0.2. When x is 1.8, y is 0.5. So what I do is I write down a table with my x and y values. And then the calculation I do for the method of false position is always the same. What's quite nice is it's the same calculation you use for the secant method. I multiply the lead diagonal values together. 0.4 times 0.5. I multiply the other diagonals together and subtract that result. So I do 0.4 times 0.5 minus 1.8 times negative 0.2. And I divide that by the second y, take away the first y. So my false position estimate is 0.4 times 0.5, take away 1.8 times negative 0.2. That's a lead diagonal, take away the other diagonal. A bit like finding the determinant of a matrix. And then I do the second y, take away the first y. So 0.5 take away negative 0.2. And it's important you get all the signs in there so you get the right things, because on the top you're actually going to have an addition and on the bottom you're going to have an addition. So when I do that, I get 0.8 for my false position estimate. Looking at the marking for that, 1 mark for your best estimate and your maximum possible error. 1 mark for going through the process of halving, that's a method mark, and then 1 answer mark for summarising that there will be 4 iterations. For the false position estimate, there's 1 mark for the calculation, and an answer mark for putting the right values into that calculation, and an answer mark for the 0.8. Next question is question 4 from the May 2011 paper, and again we're starting off with show that an equation's got a root. And this time it's still talking about iteration, but it's asking us to consider the derivative. And it's asking us to think about the derivative and say why the iteration might diverge. So for part 1, First thing I do is rearrange it to put it equal to 0 because I'm going to use a sign change. So that's my function. Stick in 0.7 I get a negative, stick in 0.8 I get a positive, so the root's going to be between the two. Now let's do this second bit, considering the derivative. Now basically all of these iteration ones where you've got x equals, using that for your iteration, xr plus 1 equals 1 minus xr to the 4, we've got x equals 1 minus x to the 4. For everything like that type, it's where the graph of y equals x crosses some other curve. Now if the other curve, in this case 1 minus x to the 4, has a gradient that is of a size that is steeper than 1, so whether it's something like negative 2 or positive 1.4 or something like that, then it will diverge. So there's my function. If I differentiate it, I get that. Now we're looking at x values between 0.7 and 0.8, so let's work out that differential between 0.7 and 0.8. It's between negative 0.2 roughly and negative 1.4. So in other words, it's always negative and it's always of a size that is greater than 1. So the size of the derivative is greater than 1. And if the size of the derivative is greater than 1, the iteration will diverge. And you're expected to know that, so you can just state that once you've found that out, the iteration will diverge. So it's all about the gradient, and it's all about the gradient of the thing on the right hand side. So you've got x equals the thing on the right hand side. You differentiate to get the gradient function. You look at the x values, and if it's always going to be something that's of a size bigger than 1, regardless if it's plus or it's minus, then the iteration will diverge. So the marking for that. Again, sign change, one method, one answer. For the differential, for actually doing the differentiation correctly, you get 1 mark. Then 1 mark for substituting in your values for x, an answer mark for getting values obviously that are bigger than 1, and an explanation mark. And that concludes this revision session for numerical methods.